Okay, so welcome to lecture 3. This is 5.3, the fundamental theorem of calculus. So in the past two sections, we know that we can find the area under the curve, or the area under the graph of a function. And we can do that in two ways. We can represent it using an integral, which is what we did in 5.2, or we could write it as a limit. So we could find this by saying we know that the area equals the limit as n goes to infinity. And then we're going to add up from I equals 1 to n. And now we're going to have our delta x times our f. So delta x is the difference in your values. So b minus a, or 6 minus 1, all over n. And your xi is a plus I delta x. And in this case, our a is 1, and our delta x is 5 over n. So we're going to have I times 5, or 5i over n. And so then I'm going to take my delta x, which is 5 over n, and plug it right there. And we're going to multiply that by the function at this value. So we're going to have 3 times, and instead of x squared, I'm going to plug in my xi. So that's 1 plus 5i over n squared times the natural log of your xi. So 1 plus 5i over n. So that is the expression for our area. And so if we wanted to know what that was and not just approximate it, we would then have to go and figure out what the summations of all these things are. And that gets really difficult. So we need something else, okay? How do we calculate these a little bit easier, right? And we know that this is the same as the integral from 1 to 6 of our function 3x squared ln x dx. Okay, we know those two things go together from section 5.2. Okay, so new set of tools. So your theorem for the fundamental theorem of calculus, which we like to lovingly call FTC, has two parts. So this is the first part. And so we have our function here. We said if f is a continuous function on a to b, then the function capital F of x is defined to be the integral from a to x of little f of t dt. Okay, so let's see. What do we know here? So first of all, you can see there's lots of different variables. So the t represents what we call a dummy variable because that variable goes away, all right? And that's because this becomes an x because your upper bound is an x, okay? So we have this statement. The other thing that's important here is that the derivative of f prime of x is equal to little f of x, and that's what's most important from the first part. Okay, so keep in mind that when one of your boundaries is an x, that gives you the function capital F of x. And when we differentiate this, we just get the function inside evaluated at that variable. Okay, so essentially what they're telling you is that the derivative and the integral are inverse functions. Okay, when I take the integral and take the derivative of the integral, I get back what's inside. Okay. Just a quick note, if f of x is the position function of the object at time x, then the net distance traveled is f of b minus f of a. So it talks about net distance, just a quick little note right there. Okay, so we want to then use this to find some derivatives. So example 1 says, find the derivative of this function. So f of x is the function, the integral from 2 to x of the sine of t to the 6th dt. So we know that by FTC, the derivative of this, so f prime of x, is going to just be the function on the inside, sine, and I replace it with the variable up here. So x to the 6th, okay? And that's it, all right? The 2 in the bottom, notice this doesn't say anything about the a that's there. Doesn't really matter, okay? Now, the x being at the top does matter, so just be aware of that. If your x is at the bottom, you're going to have to use a negative sign to flip them first, but we'll get there in the next one, okay? So you just get the derivative is sine x to the 6th, okay? The bottom one, the next, find the derivative of this one, okay? So the only thing that's different about this one is that the intervals are opposite. So first we flip the interval. We know that that's a property. So 1 plus t to the 7th, and there's probably supposed to be parentheses here, I would guess. That's probably a typo on my part. So let's assume that they're there. Okay, and now when we go to find the derivative, so g prime of x We're going to leave that negative. And we know that all I'm going to do is drop my integral because the derivative of the integral goes away. And I just get the function inside, but evaluated at that upper limit. So that means I'm going to get 1 plus x to the 7th times x to the 6th as my derivative. Okay, and this last one, example 3, slightly different, mainly because now I don't have an x, I have an x cubed. Okay, so really our chain rule is going to apply here. So the first thing I'm going to do is I'm going to flip this. So that means I get, this is the opposite of flip my boundaries. So x cubed goes up here. Sine squared t plus the tangent t dt. Okay, so when I go to take the derivative, so g prime of x, again, make sure you're using good notation here. I keep my negative. And then taking the derivative of the integral, that's going to cancel each other out. I'm going to plug in my x cubed. So that's going to be sine squared of x cubed plus the tangent of x cubed. But the chain rule says you have to take the derivative of what's inside, right? So that means we're going to take this whole thing and we're going to multiply it by the derivative of what's there. So that's going to be times 3x squared, okay? If you think about it notationally speaking, what they would do, so this is my final answer, by the way. So if you think about it notationally, what you're really doing is you can say, well, g of u is the integral from u to negative 5 times sine squared t plus tangent t dt, and u is x cubed. So g of x cubed equals that. Well, let's leave it like that for now. So when we would find g prime of x, we need to find g prime of u times du dx, because what's inside isn't an x, right? So we have to remember to differentiate what's inside. So this right here is the 3x squared you're seeing above, and this right here is the negative sine yada yada yada, okay, from up above. So moral of the story, when one of your limits is not just a plain old x or other variable, you're going to have to multiply by the derivative of that because of the chain rule. Now, the second part of a fundamental theorem of calculus is useful for us. And that is that we have, if f is a continuous function on a and b, so same criteria as before, then what we get is that the integral from a to b of little f of x dx, so our integral, so this is a definite integral with numbers at each end, notice that, is capital F of b minus capital F of a, where capital F is the antiderivative. Okay, so essentially what this means is exactly what we thought before. The derivative and the integral are inverse functions. So to undo the integral, or to take the integral, I'm going to take the antiderivative of f. And then notice I plug in my upper bound, subtract, plug in my lower bound. So what does that look like? Let's go down here. So for this example, number 4, you have the integral from 0 to 2 of x squared. So in order to do that, I'm going to take the antiderivative of x squared. So antiderivative means increase the exponent to 3, divide by the new exponent. Now, here's the notation we're going to use. We still have to evaluate this from 0 to 2. Okay. Then what it says is we want to plug our upper bound in to our antiderivative. So that means 2 cubed over 3 minus, then evaluate it at your lower bound. So plug in 0, 0 cubed over 3. And this turns out to be 8/3 minus 0, which is 8 over 3. Okay, notice that when you're taking the answer to a definite integral is a number. Okay, for the first part of the FTC, your answer is a function, it's the derivative. But when you use the second part, you're evaluating it from 0 to 2, your antiderivative, and that's going to give you a number. Okay, same thing down here with number 5. We're taking the integral from 1 to 3 of 5x to the 6th minus 4. So the first thing we're going to do is we're going to take the antiderivative. So we're leaving the 5 alone. You're increasing the power to 7 and dividing by the new power. Toss an x onto the 4. But we've got to evaluate all of that from 1 to 3. So that means we're plugging in 3. So 5 times 3 to the 7th over 7 minus 4 times 3. So all of that is your f of 3. And then you're going to subtract off what happens when you plug in 1. So 5 times 1 to the 7th over 7, use your parentheses, minus 4 times 1. When you evaluate that, by the way, that is your, whoa, what just happened? This is your f of 1. And so when you evaluate that, let's see what we get. We need 3 to the 7th, which I don't know off the top of my head, times 5 divided by 7 gives me some kind of fraction. It gives me 10935 all over 7. And then let's see, that gives me 5/7 minus 4. Oh, and I missed something. This is my f of 1, but I forgot to get the rest of this. So minus 12. And if we put all of that in, let's see what happens. We get minus 12 minus 5/7 plus 4. Okay, and I get a total of 1,553.4. Okay. All right, and that's what we get. Again, we get a value, a number answer. And this last one, let's see, we're taking the antiderivative here. So antiderivative cosine would be sine. Derivative of sine x is cosine x. Plus 1/5 x to the 5th minus 9/2 x squared minus the natural log of the absolute value of x. All of that gets evaluated from -4 to 1. So I'm going to take all of this and plug in -4. So that's the sine of -4 plus -4 to the 5th over 5 minus 9 times 8. -4 squared is 16. 16 over 2 is 8. 9 times 8 is 72. Minus the natural log of 4, right? Because the absolute value takes away the negative. Minus, you're going to plug in sine of 1 plus 1/5 minus 9 over 2. And the natural log of 1 is just 0, so minus 0. And you can put that in the calculator and get a value, and that's what your answer is going to be. And I can do that too real quick, so let's see what we get. Make sure, by the way, that your calculator is in radians. So the sine of -4 minus 4 to the 5th over 5 minus 72 minus the natural log of 4 minus the sine of 1 minus 1/5. Don't forget to distribute that negative. Plus 9/2 gives me, I get -273.97. And 1 or 2 decimal places is just fine. I'm not super picky about all that. And that's it for the fundamental theorem of calculus.